All right, let's finish this up. Let's talk about this one final idea to this central limit theorem thing and what mathematically is happening. I've already alluded to this, so this should go pretty quickly. And then we're going to do some practicing of writing out our conditions and assumptions. Here we go. So we know that the amazing thing about the central limit theorem is that no matter the shape of the original parent population, that the sampling distribution of means will approach the normal model as the sample size gets large enough. So here we go. So here's a picture of population. So we got individual x's here, and I know that it's a population because n equals 1. So look at our population mean. It's about 2, and our standard deviation is about 2. So let's watch these numbers as we move along and watch the shape of this. So this is computer simulated data so we can see what's happening. So here's a sampling distribution made of samples of size 2. So this would just be, you would take 2 random pieces from the first picture, average them, and then drop it down. Okay? And so notice our center still stays about 2. Our average is still about 2. But look at this standard deviation. It is smaller. Well, guess why it's smaller? Because it is 2 divided by the square root of n, which is 2. And that's how you get that 1.43. So see, it is less varied. The average distance from the mean is less. All right, continuing on. Here's a sampling distribution of samples of size 4. The center is still at 2. The standard deviation now is only 1, because that's 2 divided by the square root of sample size 4, and that's 2 divided by 2, that's 1. Look at this, 9. Sample size is 9. 2 divided by the square root of 9 is 3, so 2/3. So the standard deviation is now 0.6, 2/3, 0.67. And it's getting to looking better. Here's samples of size 16. That's for the standard deviation. See, the center is still the same. The mean of the x bars is still the same, with the standard deviation 2 over the square root of 16, which is about a half. Not quite a half, but pretty close. Okay. And here we go. Samples of size 25. Getting closer. Look at how good we're getting. We're getting closer. Center is still at 2. And 2 over 5 is the standard deviation, and that is 0.4. All right. Now, this one does 40 because some textbook, this simulation that I got this page from, some textbooks say large enough is 40. Ours say 30, and those are two both well-known numbers. So AP and College Board accepts either. They know you are stating a common criteria. So whether you're setting it large enough as 30 or 40, it doesn't matter. So here we go. 2 is still the center. And look, we're getting even a smaller standard deviation. You can see here, sampling distribution of samples size 100 is 2/10. So, all right. But again, look at what happens to, okay, so here we go on the left. Final idea. Look at what happens to the shape of the graph as the sample size increases. So we know it approaches the normal model. The mean stays the same. The variability gets smaller, and by the square root of n. And of course, once it reached large enough, then it's approximately normally distributed. Okay, so let's now see, okay, how does this really look with a problem? And what you're going to do on your assignment and what you'll practice today is you'll practice writing out the conditions. These are actually on problems that you have already done, the question 2. You've kind of already, we did backwards. We did the problem and understood the problem, and now we're going to go, okay, yeah, let's make sure we state the conditions for that. So we're going to describe the distribution. You remember our describing the distribution, what we have to have for that describing the distribution is our socks, but we don't really have this outlier component, shape, outlier, center, and spread without the outlier component. All right, so that's what we will do. And in order to take care of this shape component, that is going to be our, I think what I want to do is get me some of these things going on. So in order to do that shape component, that's our random, independent, and large enough. Okay, so here is what we'll see. Here's how that'll work. Here we go. So here's our shape. Random, stated, or assumed to represent the population. Okay, so here we go. Let's see. So random, stated, or assumed to represent the population. So we're assuming, because it didn't state, to be random selection of the blood recipient patients. Oh, this was a problem that we had in an earlier problem about the hepatitis infection. Okay. Okay, independent, N is less than 10% of the population. So we write the word independent. And then these were samples of size 2,000. And 2,000 is less than 10% of all such blood recipients. Okay, problem number one that my students do, they are negligent and they just leave off this part here. Okay, I have nothing extra written here. You cannot say 2,000 is less than 10%. Because the last time I checked, 2,000 is not less than 0.10. Okay, it is less than 10% of all such blood recipients. And there's a difference. So don't you dare leave all this part right here in orange, or I will be marking it wrong, because these are the little things that my students have a tendency to leave off, and I know to look for those when I'm grading them. Large enough is tricky because it all depends, mean or proportion. Was this a mean problem or a proportion problem? Well, it was a proportion problem because it talked about the 4% infection rate, and we were trying to reduce that infection rate. So, therefore, my rule for proportions is at least 10 successes and at least 10 failures. Has to be large enough. So, notice for independent, my inequality is less than. But for large enough, my inequality is the greater than. And I have nothing extra written here. N times P, and it's true P, not your P hat. And I put what that equals, which is greater than or equal to 10, and then the N times the 1 minus P. So the 4% was success, 96% is failure, and I put what that equals, and that's greater than or equal to 10. So upon these being met, which I think is reasonable, then the approximately normal model applies. All right, so there is shape of our socks. Now the other part falls easily enough. It's center. You can just, you wouldn't even have to write this out in words. You could just kind of like write this right here. You could just take that and put it right there for center. Okay. And then for spread, the spread is the, well, hold on a second here. Didn't get that down there. Okay, so for our spread, then that's also the standard deviation. So what you could do is then take that information that you have over there on the left. So I could go like, oops, I don't want to do that. So I could take that section there and here, and I could just put that right there. So I write center and I put that formula from the orange section. I write spread and then I put that standard deviation of the p hats there. Okay. All right. And again, notice that the large enough for proportions and for the means is different. Okay, which we'll get to the mean problem here's next. Okay, this is a problem we've seen on an earlier assignment where we were talking about the size of the board that the machine was cutting. On average, what's the length? Okay, so we're going to not, so it asks us on the assignment, it asks us to identify if they're the mean or proportion problem on the homework, and this was a proportion problem, and this second one's a mean problem. And then identify socks or describe the distribution. So that's going to be my socks without, I don't have outliers to note. So I'm going to come over here and shape is going to be my random, independent, and large enough. Okay. So my random, it was stated in the problem that it was a random selection of the 1 by 10 boards from the lumber yard. Okay? Write the word independent, and N is less than 10% of the population. So my sample size is 60 boards. So 60 is less than 10% of all such 1 by 10 boards. So in essence, what I'm also doing is indicating to the reader what the population is. And so the population is all these types of 1 by 10 boards. Okay. I could put from this lumber yard, didn't have to. But don't just put 60 is less than 10%. It's 60 is less than 10% of all such 1 by 10 boards. Okay. Large enough is tricky because it all depends. Mean or proportion. Means is 30. So in our case, 60 is greater than or equal to 30. So the nearly normal model applies, or approximately normal model applies. All right, that's the shape. Now coming on down to the center and the spread, and you don't have to write it out in words. Again, you can do this right here to do you can just write that formula for the center, and then you can do this for the spread. Okay. All right. That's how you do this. So then what that means is on your assignment then what you're going to be doing is identifying what type of problem it is. So you're really just practicing these conditions. Okay? So you're going to identify the problem. It says right here, determine if the scenario is representing a proportion or a mean. Okay. Then write out and verify the assumptions. So that's part of describing this distribution. So that verification of the assumptions is really the shape part of our socks. Okay. Do not work out the problem. I think all of these problems you have already worked out in prior assignments or notes. So none of them should be new. But now we're just going back and verifying the assumptions and describing the distribution. Now that we know that part. All right, so there you go. Good luck on and I think it is just 5, oh, maybe there's 6 of these. Yay for you. 6 that you get to do. It's probably 3 means and 3 proportions, I bet. And so there you go. Good luck to you on describing the distributions and your conditions.